Hello, everyone. My name is Bakaris Abadir. I'm a senior software developer with IQVIA, and today I'm going to present top-down specialization using Apache Spark. So today we're going to go over k-anonymity theory, which this work is based on, followed by an overview of top-down specialization algorithm, how the data was pre-processed, how the algorithm was adopted for Spark, the test environment that I used, key results from my experiments, and key takeaways that I learned. So before I begin, I would like to acknowledge the two papers that this work was based on. The first one was Top-Down Specialization for Information and Privacy Preservation by Fung and Wang from Simon Fraser University, along with Philip Yu from IBM Research. And the second one is the Top-Down k-anonymization implementation for Apache Spark, which was the first paper that attempted to adopt this top-down specialization algorithm for Spark, where I based my work on and I aim to assess. So what exactly is k-anonymity? So k-anonymity basically is a privacy-preserving data publishing theory that aims to protect personal data before a data set is shared for secondary use, such as research or analytics. So it basically states that a data set is called k-anonymous when for every record, there's at least k-1 records with the same quasi-identifier values. So quasi-identifiers are basically those attributes that when we look at them on their own, they cannot identify an individual, but when they're used collectively, they can identify an individual. So if we look at this data set, for example, we see that there are two females with grade 12 education who live in Nepean, two other females with an associate degree who live in Canada. But however, we do see three unique records that can identify an individual. So an adversary, for example, who with a pre-knowledge of the existence of a male from Orleans with a master's degree will be able to tell that they make $50,000 a year. So in this case, the quasi-identifiers are the education, gender, and city, and the income is what we call a sensitive attribute, which is the attribute that we're trying to protect. So how can we make this data set satisfy k-anonymity? We notice, for example, that the bachelor's, master's, PhD can be generalized to the same parent value, which is post-secondary. We also notice that Chapel Hill, Orleans, and Beacon Hill are all three neighborhoods in the Ottawa East area. So what we can do is that we can cross out these 6 values and then replace them with their parent generalized value, which in this case is post-secondary and Ottawa East for education and city. So now the same adversary will not be able to tell which one of these 3 records are the male with the master's degree from Orleans. So therefore, they will not be able to tell what their income is. And this data set is now too anonymous. So that means for every record, there's at least one other record with the same quasi-identifier value. So what exactly is top-down specialization then? So it is a way to achieve this generalization that I was talking about, but in a way that aims to balance data utility and privacy. Because as the data becomes more private, it becomes less useful for research or analytics. So for every attribute that we wish to, for every quasi-identifier attribute in the data set that we wish to anonymize, there's a corresponding taxonomy tree. So a taxonomy tree is basically a hierarchy that represents the classes that all the distinct values belong to. So what we're looking at right now, for example, is the taxonomy tree for the education attribute. So the root node is the most generalized value, and the leaf nodes are the distinct values are in the data set. So top-down specialization goes through each level of that tree, which we're going to call anonymization level from now on. And it aims basically to keep specializing values. It starts with the most generalized, starts from the root node. It keeps specializing the values until K is violated. So until the data is very specialized. At every level, what we're going to also call an iteration. So every anonymization level is an iteration in the algorithm. For every anonymization level, it calculates what we call a score. So the score basically comprises information gain per privacy loss. If I were to specialize this attribute to this anonymization level, how much information will I gain versus how much privacy will the data set lose? So for example, I pick all the values that belong into the left subtree, and I generalize all those to without post-secondary. And on the right subtree, I take masters, for example, and doctorate, and all these values from the leaf node on the right subtree, and generalize all those to post-secondary. I make the calculation, calculate the score, and I do this for every quasi-identifier attribute, and the attribute with the highest score is the attribute that will end up specializing. And I keep going all the way from the top down until K is validated, and then we stop, and this will be the our k-anonymous data set. So pre-processing of the data set involves removal of all the non-quasi-identifiers so that our data set is basically narrower. So from now on, I'm going to refer to quasi-identifiers as QIDs. And so those QIDs and the distinct values of SAs, which is the sensitive attribute in our example was income, these are all grouped together with the count. Also, to make it a little bit simpler, instead of using the numeric value of the income, we're going to use a binary value for less than or equal 50,000 versus over 50,000. Once we have that, as you saw from the top-down overview, is that this is a very iterative algorithm. So we are going to go through that tree over and over again for every anonymization level. And calculate that score. So it would be neat if we can find the parent for that this particular distinct value belongs to without having to traverse the tree over and over again in runtime. So it'd be nice if we can do that actually in constant time. So in order to achieve that, we do what I call building a path map. So we're going to traverse the tree in a breadth first manner. So we start from the top, and we're going to maintain a queue on the left-hand side along with a map on the right-hand side. That map is basically the child-parent mapping for every child and what their parent is in the tree. And the queue on the left-hand side, it will contain the number, the node that I'm traversing as many times as if they have child nodes. So in this case, for example, in the first level, I'm traversing the node any, so I insert any twice to that queue because any has two child nodes without post-secondary and post-secondary. And then I keep moving to the next level. And when I traverse without post-secondary, I pop or dequeue one element from the queue. And this represents the parent of this particular node. So on the right-hand side, I have the child-parent mapping. So I'm saying, okay, without post-secondary's parent is any. And then I traverse post-secondary, and then I pop or I dequeue another element from the queue, and this also represents any or it represents parent for this particular node. So I have without post-secondary's parent is any, and post-secondary's parent is also any. And while I maintain that queue, you notice that I inserted without post-secondary 3 times because without post-secondary had 3 child nodes, and I inserted post-secondary 3 times because it also has 3 child nodes. And I keep going through all these levels until I end up with an empty queue and a child-parent mapping, as you can see on the right-hand side. So for example, preschool's parent is without post-secondary and so on and so forth. Now with that map, I can recursively go through it and build a path basically from all the distinct values all the way to the top. So for example, if I'm interested in finding the path for a 9th grade element, I know that its parent is junior secondary, whose parent is secondary, whose parent is without post-secondary, whose parent is any. But since we're traversing that tree from the top down, so I simply reverse that path. And now I have the 9th grade. In order to get to the 9th grade, I go from any to without post-secondary to secondary to junior secondary, and then to the 9th grade. So now with these path maps, I'll be able to tell what the parent or the anonymization level that I'm at for every element in constant time, because basically it's a key lookup with the 9th grade, which is the value in the data set. I'll be able to tell that the parent right away is any, and then without post-secondary, and so on and so forth. So how is this adopted for Spark? So basically, before we start, we needed to generalize all the quasi-identifier to the root of the anonymization level. So any is always the root for all the taxonomy trees. So in this particular example, you will see here that education, gender, and city are all generalized to the top of the taxonomy of the corresponding taxonomy tree, which is any in this case. I'm also maintaining the aggregate for every collection of quasi-identifiers. So for example, the count or the aggregate of records with all any is 21, which is basically the whole data set. Once I have that, then for every anonymization level, I need to calculate that score, which basically involves the information gain and privacy loss. It uses a formula whose parameters are plugged in using these aggregates. That's why we need all these aggregates, so that we can calculate the information gain and privacy loss for at every level. So we have education, for example, there are 7 records that can be generalized to without post-secondary. We have 14 records that can be generalized to post-secondary. And we do the same thing for city, and we have the corresponding aggregates for both east and west. And now, once we have that, we need to score the best option. So all the anonymization level values are aggregated at every partition, and then they are merged into a single row table with the totals. So I need to basically compare the score for education versus the score for city using these aggregates. So now I have here the city, and I compare the aggregate with education. So, and then once I have all the aggregates, I need to basically merge all these aggregates from all these partitions into one row data frame that has all these aggregates. So the Y and the N represent the aggregate of the records that can be generalized to any that has over than $50,000 as a sensitive attribute, which is the income in this case. And the N represents the second value of the sensitive attribute, which is less than 50K. So for example, there are, if I start from the top, there is 21 records that can be generalized to education any. There are 12 records that can be generalized to education any with over 50,000 as the income. 9 records that can be generalized to any with less than 50,000, and so on and so forth for every node, as well as its children. So the idea is that we want to know what the score is, or what the information gain per privacy loss, if we were to specialize this any node to its children, which is in our case was without post-secondary and post-secondary. So we do with this for all the quasi-identifier attributes. I only included the example from education because, as you can see, this will be a very wide data frame. So I only included the aggregates from education as an example, but this will be for all the quasi-identifiers that we aim to compare. Once we have all these numbers, these are basically plugged in to the formula that calculates the information gain and privacy loss. And now I have that one final number that tells me what's the score if I were to specialize any from the education attributes to its children of without post-secondary and post-secondary. And I do the same thing for all the other attributes. Once I have my best option, I need to then reiterate. Before I reiterate, let's say, for example, that city is the highest score anonymization taxonomy tree. So I need to basically remove the root and take its subchildren and add them to the anonymization level set. So in my next iteration, I'm no longer comparing 2 anonymization level trees. I'm comparing now 3, which is basically the subchildren of the highest score taxonomy tree, along with whatever other trees that I have in the set that basically did not have the highest score. So I keep doing this until basically K is violated, and now I have my final score. My final data set with all the generalized, or with all the specialized attributes using these iterations. So how was this adopted for Spark? So basically it started with a pre-processed data set that was transformed to partition data frames. So the pre-processed data set is the example that we saw earlier, which basically has these group by and count data set. And then we start partitioning all these this data set to n number of partitions. I'm going to go over the partitions as well. but we basically go over n number of partitions, and we calculate the aggregates, prepare the sum function, sum map functions, which is a built-in Spark function, to calculate the aggregates um, for every attribute that we are looking at to calculating their score. And then once we have these map functions, then we collect to one single row data frame that we saw here. And now I have all these total aggregates collected, and now I have my parameters that I can plug into the formula and calculate the score for every attribute and for every anonymization level. And we use this, the Spark's two local iterator function in order to come up, or in order to collect these aggregates to one single row. So I ran multiple experiments basically to assess the parallelization of this algorithm, or how well it parallelizes on Spark. So which was the main actually outcome of this project is that assessment, to see how well it parallelizes. So before I begin looking at the results, I need to tell you what my test environment is. So basically I used an OpenStack cluster with 32 gigabit of a gigabyte of disk, 8 gigabyte of RAM, and 4 virtual CPUs per node. The K was always set to 100, and I ran these experiments on 1 node, 2, 4, 8, and 16 nodes in the cluster. I also used data set sizes of 250,000, 5, 10, and 20 million rows. The Spark manager that I used was for these experiments was the standalone, which comes out of the box, version 2.4.2 at the time, with Scala 12 and Java 8. And the dataset is called the adult dataset, which appears to be a very popular dataset for privacy-preserving algorithms research. So basically, it's very similar to the examples that I use. It has demographic data of education, city, marital status, gender, all sorts of different demographic data. But it was only 32,000 rows, which was obviously not enough to assess any parallelization data, experiments. So I enlarged it by generating random values from the list of distinct values in the original data set to come up with this these different variations of different sizes of the data set. In my experiments, I also used 8 categorical QIDs that were tested that we aim to assess its score and anonymize. So the first experiment that we wanted to look at is what's the n number of partitions that we can use to achieve the best runtime. So for this experiment, I used the 8-node cluster and the 5 million row data set. So as you can see here, we ran this experiment 8 times. The best performing was 32. In this case, if you recall my cluster, every node had 4 virtual CPUs, or 4 virtual cores. So the best performing number of partitions was 32, while the default was 200. So as you can see, the best performing was a lot lower than the default that Spark came with. So these experiments were necessary in order to see what the best performing partition is, and this number was always used for all the experiments. So when I ran one experiment on 1 node, I used 4. On 2 nodes, I used 8 as the number of partitions, and so on and so forth, all the way until my 16-node experiment. The next one was assessing the speedup. So I ran the speedup tests on all the 4 dataset sizes that I mentioned. So the first one was 250,000 rows dataset test. So as you can see, the bottom line here is the optimal runtime. So you would expect, if you double the number of nodes, your runtime will be cut in half, because every node is dividing the work. But as you can see here, this was not achieved with the smaller data set of 250,000 rows. The actual time frame, the actual runtime was far away from the optimal. And as a matter of fact, going from 2 nodes to 4 nodes did not improve the runtime at all. And going from 8 nodes to 16 nodes also had a flat runtime. The runtime was not reduced at all. So there are 2 theories that could explain this behavior. Is that the first one is that when your partitions are very small, the overhead of the partitioning and the network traffic is basically outweighs the benefits that you will get from the runtime because every partition is very small. The second theory is that all this data set was partitioned over a randomly generated unique ID. So it's possible that a custom hash function could have helped in these small size data sets to achieve better parallelization. As you notice here, as we keep increasing the data set, the actual runtime the gap between the actual and optimal runtime gets very close together. So for the 5 million row data set, it's very close to optimal, but not yet, quite yet, because as you can see, also from going from 8 nodes to 16 nodes, the runtime was flat. It did not cut in half. The story gets a little better if we keep increasing the data set. So for the 10 million row data set, it got even closer and even better for the 20 million row data set, which is the closest that we could get to the optimal, as you can see from this graph. So the scale-up performance is basically another way to interpret the previous slide or the previous result for the 20 million row data set. As you can see overall, when the 100% increase in the data set size only resulted in like 55% to 65% increase in time. And this could be also explained by just by the speed up graph, is that going from 10 million to 20 million row, now every node is doing a lot more work than before. And that's why the runtime did not significantly increase. And as a matter of fact, remained almost virtually flat if you compare it with the data set size increase. So what did I learn from these experiments? So there are multiple key takeaways that I learned. The first one is Spark is actually best suited for iterative algorithms, such as top-down specialization. There was actually a research paper that I came across during my literature review when I was working on this project that compared MapReduce framework with Spark for iterative algorithms. And it found that Spark performed up to 5 times better for iterative algorithms because you can take advantage of all the caching and partitioning features that come with Spark out of the box. The second point is that there's no magic number for partitions. It has to be analyzed for every algorithm and for every data set size. I also came across a lot of literature that were saying twice the number of cores is what you want to set your partitions to. These numbers are all algorithm specific. As you can see, in my case, double the number of cores did not actually perform poorer than n number of cores when I set the partitions to n number of cores. The other thing is the data set size. So there's no guarantee that beyond the 20 million row data set, I would have been able to use also n number of cores for my partition numbers, because it could have, for like 40 million rows or 100 million rows, it could have crashed if I kept the number of partitions at n number of cores. So it has to be analyzed for the data set size that you're using. It also has to be analyzed for the algorithm that you're running on Spark. The third point did not really have a significant improvement over in my runtime or my performance, but it was significant enough to put it down, is that if you're familiar with Scala's tail recursion, there's a lot of optimization that comes with tail recursion over loops for the code that runs on executor. So in my implementation, for any code that runs, for any iteration that runs on Spark executor, I used tail recursion instead of for loops. And also from a developer perspective, tail recursion is fun to work with than boring for loops, I guess. The next 2 points are almost related. So the first one, in hindsight, it was not very surprising. We should always aim to minimize the number of operations or collect calls, such as aggregations, to only a maximum of 1 per iteration. Obviously, this depends on the algorithm, so you may not have the luxury to minimize them all to 1 aggregation per iteration. But in my case, that was good enough, and that's why I had this wide data frame that I collected from all the partitions. And that's why I have only 1 map function that aggregates them all at the same time. And collect calls to a wide data frame was actually performing much better, up to 16 times better in terms of runtime than if I do small aggregations on every partition. So my brute force attempt was that, okay, it makes sense that it would perform better if I run these small aggregations on every partition so that I have less to work with. But actually, on the contrary, having that huge collect calls from all the partitions to a single row data frame using the two local iterator call actually had 16 times improvement in the runtime. And my last point is the hash function. So the partitioning over unique ID, as you can see, achieved close to optimal speedup for data sets larger than 5 million. But what about data sets that are less than 5 million rows or 5 million rows and less? Can a custom hash function help with partitioning on smaller data set? So I guess this is a point for future research to consider. So all the implementation that I talked about, the resources that I used in my research are on this page. I'm going to pause here for a couple of seconds if you want to write it down, or you can ask me in the chat. I'll be happy to share it. Some of the papers there are behind IEEE and ACM firewall. So, but again, if you may be able to get them from Google Scholar if you're interested in one of the papers by the title. And also you'll see the experiments spreadsheet that I have for my experiments, and as well as the actual implementation. So that wraps it up for me. So if you have any questions, feel free to ask. And please don't forget to rate the presentation. Thank you very much.